Hi, in my previous lectures I was talking about E and Z isomers of alkenes, and imagine a flat molecule like this paper with QW, X and Y as substituents. You see that this is flat and it has a mirror plane, and therefore this cannot be chiral because you can just slash it along the axis of the paper to cut through all the substituents. You can slash it from here. If you cut it through here, you can cut it through here. So that's for this cannot be chiral. So every molecule that is planar cannot be chiral. However, if something happens to this and then it's twisted slightly like this, for instance, then we will have a situation where the Q and W and X and Y are not pointing, are not showing up at the same time. At one point you see Q and W, but you will not see X and Y. And then when you see X and Y, you cannot see Q and W all at the same time or in the same phase. You can say that the molecule or compound is chiral even though it doesn't have a chiral center. In that situation, we call that situation AXIAL chirality. Okay. So over here you see that X and Y are pointing like vertical, and then Q and W are horizontal. And again, in the same situation, if Q and W are vertical, X and Y are horizontal. So this is just the simplest example of AXIAL chirality. And the best way to illustrate this is by using models or model kits. So the simplest one I'm going to use is an allene versus an alkene. So let's see, this is an alkene. Okay, this is an alkene. It has substituents around 8. And you can call it cis or trans or E or Z, it doesn't matter. But this is flat, so any point in time, even though you can't cut it through here, but along the plane of the board, you cut through, you get a plane of symmetry. So this cannot be chiral because of plane symmetry. Yeah, plane of symmetry is along the plane of the board. Okay, so let's try something different. I'm going to draw an allene. Okay, this is an allene. Or a structure that looks like an allene. That is 3 carbons and then having double bonds or 2 double bonds in it like this. Now here this molecule is not flat because of the situation. This is pointing towards me, this pointing away from me, but over here the side is in the plane of the paper, so it's like it's twisted like this or like this, so there's no flat. So if you cut through, you will not get equal halves. So this is chiral, and this kind of situation is what we call axial chirality. Now, because it's chiral, therefore we can assign RNS configuration to this, and to do that we need to look at substituents and their priorities. So I'm going to assume, alright, that this, to check, you need to check on each carbon which substituent is of higher priority. So let's say A is high and then this is lower, and then this is, let's see over here, this is higher and this is lower. Okay, so after doing that, then you look at the molecule and how the substituents are arranged. You see that if I'm looking at the molecule from here, okay, I'll see A and B first, and A will be on my right and B will be on my left. And then behind it will be A prime, B prime. Okay. Now in that case, A prime will be better than B prime will be down. Now the H and the L stands for high priority and lower priority on each carbon. Okay. Now after doing that, because I started from this, looking at this carbon facing me, I need to start from that side. So I'm going to start from B and A first. I need to start from the substance that is lower priority first, which is, in this case, is B. And then after that, I need to look at the other substituents and see which of them is of higher priority, and then move from a lower to the higher priority. So from the horizontal substituents pointing in and out, I saw that B is a lower priority, and from the vertical substituents pointing up and down, I saw that A prime is higher priority, so I have to go from the lowest towards the highest. Okay, so in this situation, I'm going clockwise, so this will be R, and therefore this is an R isomer. That's right. And the same thing will happen if I'm looking at the molecule from here instead of from the other side. If I was looking at the molecule from here, if I was doing that, then I'm going to have a different arrangement but the same answer. That is, I will see A prime and B prime first. And B prime. So again, the H and the L stands for higher priority and lower priority. And then I will see A and B behind now. If I'm looking at it this way, then I'll see B on my right, and then A will be on my left in that case. Again, the H stands for high and then B stands for low or lower priority. So since I started looking at the molecule from this side, I saw A prime and B prime first. So that's why I need to start A prime and B prime. Which one is lower priority? Of course, I know that is B prime. Okay, now look at A and B. Which one is high priority? And then assign the A as the high priority. So in this case, I have to go from B prime to A, and that is still clockwise. So this is R, and that's the same as we got by looking at the molecule from here. So this is an example of an allene, or a structure that looks like an allene with axial chirality. So again, you can draw the enantiomer with this. It will be very easy to draw, and that enantiomer will have the opposite configuration. So I'm going to draw the enantiomer. It will look like this, and then so it's very easy. So if I want to check the system that I've been using, I can just look at the molecule from here. Okay, so if my eyes is pointing that way, then I will see A prime and B prime first. Okay, so A prime. Okay, and then I'm looking at this from the side, and B will be on my left, and then A will be on my right. Okay, so having done that, all that I need to do is, since I was looking at A prime and B prime first, so B is my lower priority, and then check A and B, which one is high priority. So I need to start from this lower priority and go towards a high priority, and that is counterclockwise, so that is an S. So this was R, and then this is S. So that proves that the method I'm using is correct and perfect, and that's the method that you have to use for every situation like this Allene axial chirality, where you have to determine its hardness configuration. So this molecule is chiral, but it doesn't have a chiral center. It's chiral because of the way it's twisted. Okay, so we will do more examples. Okay, so I wanted to try with specific examples. Okay, so I'm going to assume we have a compound that looks like this. And on this carbon we have bromine and a methyl group. Of course, bromine has a higher priority than a methyl group. So this side I'm going to call this, say, A, H, and then this one will be PL, something like this. And then this side you call A prime. And this side will call A prime. And this will be B prime. So the bromine is higher in priority than the methyl groups. Okay. So after assigning them this way, I'm going to assume maybe I'm standing here, I'm looking at the molecule from here. Okay. So I will see these two groups first, the A and the B. So looking at this, bromine is pointing to my right and the methyl group is pointing to my left. So I'm going to write this. So the H stands for high priority. And then the B or the L stands for lower priority, because the B is what I'm using to represent the methyl group on this side. And then behind this I will see this bromine and this methyl group along the vertical plane of the board. With the bromine pointing up. And then down below is the methyl Okay, so what we do is, since I started looking at this group first, this bromine and methyl group first, and these are in the equatorial, the left and right on this board, I have to start with these groups first. And over here, the methyl group is my lowest priority, so I need to look at that. And then after that, I need to look at the other group. I have bromine and methyl group on the other group. The bromine is the highest priority on the group. So I have to start by looking at the lowest priority of my starting point, and then move towards the direction of the higher priority of the other group behind me. So from lower priority in my starting point towards the higher priority of the other group, I have to go from this methyl group towards this bromine, and therefore that is clockwise, and that is R. So this is R. Okay, and again I'll get the same answer if I started the assignment from here instead of here. I'll get the same answer. Okay, so always start from the lowest priority of your starting point, and then draw the arrow towards the higher priority substituents of the next group. Okay, so I'm going to draw it's an enantiomer. Okay, so the enantiomer of this will look like its mirror image. So this is a mirror image of this, and again we can go ahead and assign this RNS configuration. So let's call this A cos high priority. Let's call B priority. Let's call this A prime high priority, of course, and then lower priority, and then again we can go ahead and then look at it. So I'm going to assume that I'm standing here. Okay, if I stand here, this group and this group in the vertical plane of the board, this and this are pointing in and out towards me. Now I can draw something like this and put this edge because they are in the vertical plane. Then this group pointing in and out will come behind it. So looking at this, this will be on my right and this will be on my left. Okay, now the L and H stand for lower priority, and higher priority on each specific carbon. So I started with these groups, the A and B groups, which are up and down here. So I need to start from the lower priority in that group and go towards the higher priority of the other group. So I need to move towards this direction, and that is counterclockwise. So that is S. So this is an S. Okay. So that's how we assign RNS for allene compounds, or compounds that look like allene. Again, we can try different compounds. Let's try a different situation. Alright. So assuming we have a compound like this, we can look at here and here, which of these two has the highest priority. Of course, is this. So let's call this A, and then let's call this B. Okay, over here the bromine has higher priority, here the OH has a lower priority. And over here on this carbon we have the methyl group has the highest priority. Let's call this and then this hydrogen has a lower priority here. Okay. Now if I'm assigning the RNS, I'm going to assume that I'm standing here and I'm looking at the molecule on this side. Okay, let me change it. Let me rather take it from here. So if I'm standing here, I will see these groups, the methyl group and hydrogen first, and this group pointing in the vertical plane of the board. So I'll see AH, A prime, then B prime. Of course, the L and H stand for higher priority and lower priority. So the twins, and then behind them I will see the OH and the bromine. Now of these two, if I stand from here, how will I see this? This will be on my right. For BH stand for higher priority, and then the A over here will be on my left. Okay, so I'm standing here, I'm looking at the molecule. Okay, so this will be behind this carbon. So because I started from here, I need to start the assignment from here and here. So of this and this is the lower priority, so I start from there and I move towards the higher priority of the other substituents, and therefore of this and this is high priority. So I move from the lower priority of my starting point, or my starting point, towards the higher priority of the other group. So this is counterclockwise. So this is S. Therefore this is S. Again, I can draw the mirror image of this. And then I was saying the priorities on each carbon. So on this carbon we have the methyl group is my high priority, and the hydrogen is my lower priority. And then on this carbon, this going to be my lower priority, and this is going to be my high priority. The bromine has a high priority over the OH. So I'm going to assume that in this situation I'm looking at the molecule from here. So if I look at the molecule from here, I will see OH and the BR first. So and then now this is pointing in and out, or this is pointing up and down. So because I'm looking at this first, I need to draw the horizontal for the in and out. Okay. So if I stand here, the bromine will be on my right. This is a B prime H, and then the OH will be on my left, which is the A prime L, and then behind it is going to be my methyl group and hydrogen. So A okay. So since I started with this group pointing in and out towards me, that is A prime and B prime, to start from these two, which of them has lower priority? Of course is the A prime. Then move towards the A and B, which one has high priority? Move towards that one with high priority. So that means I need to go from here towards here, and that is clockwise, which is R. So this is R. So that's how we assign RNA's configuration for allene or allene-like compounds. Now there is a situation where the allene will not be chiral. That is, if any of these groups are the same, if these two are the same or these two are the same, the allene will not be chiral to have a plane of symmetry. So let me show you the situation where the allene will lose its chirality. Okay, so if on each carbon or one of the carbons the two groups are the same, let's say we have A and A here, and let's say this is B, and so this is A prime and this is B prime. So even if these two groups are different but the groups on this carbon are the same, we will have a mirror plane. That is, you can cut through this in a vertical plane, you get two equal halves. So this is not chiral because of the vertical mirror plane. And again, the same situation if this was different, but this is the same on this, we will have, in that case we will have a horizontal plane of symmetry, and this will not be chiral too, because you can cut through like this and you get two equal halves, and this will not be chiral. So this is the situation for allene, and one is chiral and one is not chiral. For this to be chiral, you should have two different groups on each carbon, or we can have three different groups, or other groups can be completely different. Then we have a chiral allene. Otherwise, if one carbon carries the same group, then the molecule will not be chiral. Okay.